Hello, everyone. Welcome to the Evident webinar, Find Flaws Fast. We're going to be speaking about inspection technologies applied to the automotive sector. So first thing, before we start, let's just see how this session will work. First thing is this webinar will take approximately 1 hour. So the presentation will last for around 40 minutes. And then after that, there will be questions and answers. Me, myself, and my colleague will be talking and answering your questions. So if you have any questions, there is on the webinar platform where you're watching the webinar, a box for questions. Just write the question there. And at the end of the session, we are going to go through your questions. So if you have anything, just write down the question and we'll cover that. Everyone's microphone will be muted. So it's going to be myself and my colleague speaking during the presentation. And then we go to questions later. And there will be a recording of this webinar as well. So after this webinar, if you want to watch it again or you want to pass to someone, there will be a recording. The other thing is, as we mentioned, this webinar is recorded. So please, when you participate of this webinar, you're consenting to participate and have your presence recording through the questions. Now going to the webinar, first thing, who you're speaking today with. Myself, Bayard Morales, I'm chairing this webinar and I'm going to speak as well. So I'm the marketing manager for remote visual inspection in the European, African and Middle Eastern region. And with me online is my colleague Angelique Raoud, which is the marketing manager for non-destructive testing technology. So today we're talking about two different technologies applied for the automotive. We're going to start with remote visual inspection, which is with me. So first thing is a brief on Evident, right? So what is this brand, who we are exactly? Then we go to remote visual inspection, and then after that, the entity, technology and case applied for automotive industry. Just so understanding who is Evident, we are a company that provides a number of solutions, especially inspection solutions in the industrial and life science markets. Our company is a subsidiary of Olympus, 100% owned by Olympus. And the objective is really like our technology objective is to make life of people healthier and safer where we work and when we play. And the idea is really, as we're going to see here, all the technologies involve innovation and exploration. This is about being able to see things that normally you wouldn't see. And that's where the tagline "seen is solving" comes into play. As I mentioned before, we have two main divisions. One is the life science business, where you have all sorts of microscopes and equipment applied for life science research, and you have the industrial business. My colleague and myself, we're part of the industrial business, and then there is really a vast number of sectors where the technologies can be applied. The first technology that we're going to speak is remote visual inspection. And just for us to know exactly what we're talking about, let's go to the basics quickly. We are going to be talking about industrial endoscopes. And when I say industrial endoscopes, it can be a very different number of types of equipment. What we can see here, like for instance, videoscopes, fiberscopes, and rigid borescopes, which each of them, they have their own particular characteristics. The rigid borescopes, for instance, ones that we see here on the bottom, this is where the technology started. It's the simpler equipment. It's just really an optical equipment that needs straight access to where you're inspecting, very commonly in many applications, especially in the past. And then you have fiberscopes, which already have a flexible probe. And then you have finally the videoscopes. What is important for us to see is what is the difference between all these technologies. All of them, the objective is to be able to see inside machinery without having to disassemble. But on this slide here, this presents a summary of the differences, right? And many times when we are working with remote visual inspection, we're going to say, oh, yes, borescope inspection or endoscope inspection. but we actually meaning different equipment. So on this presentation today, we are going to be mainly looking at video scopes. And the reason why is that, as we can see on this table, this is the most versatile and that's the most modern type of technology that we can use for automotive inspection. Traditionally, in the industry in the past, rigid borescope was the dominant technology because it's simple, it was not very expensive, but the limitations of the rigid borescopes when you compare to the video scopes make the video scopes the dominant technology now. Fiber scopes are still used, but I would say even less than the rigid borescopes for automotive inspection. So really we are going to be looking at the video scopes. These are the ones that you have flexible probes. Everything is built in a single unit, a single equipment. So you have the light source, image acquisition system, optical system, everything is in one unit. So that's why we're going to focus on the video scopes. Now looking, for instance, what we have in terms of portfolio of products, we have at the moment 5 different products. So what you see here on the left, the first one is the iPlex Lite. That is a handheld video scope, very common with many customers in the automotive sector. It's robust, simple to use, perfect for that use. Then you have the iPlex GT-GX. That's also very common with automotive customers. And then it's particularly common with customers that are doing research and development on this area. And this one has a little bit of a balance, has a larger screen. The remote control is separate, as we can see here. And it has a little bit more of capability in terms of imaging and light. And then you have the iPlex NX, which would be the ultimate level of quality in terms of image and light. So these 3 here are the video scopes that we consider the core, because they can be used in pretty much any sort of application. And then you have the other 2 video scopes, which are more niche. So the one on the top is called iPlex DX. And the main characteristic is a 2.4 millimeter diameter probe. So it's very thin and still is articulated. And this one also see quite a lot of application in automotive inspection, because of the many times, especially in cast parts like engine blocks, you're going to have very small orifice holes that you have to go through. And you have also the iPlex GR, which is not really for the automotive sector. This is a very long video scope, 30 meters long. See, this is a lot of applications in oil and gas and nuclear and power generation. But probably you and in the automotive inspection world will be looking probably mostly about the G-Lite, iPlex G-Lite, iPlex GT-GX, and iPlex TX. So since now we've seen more or less what we have, let's go directly to the cases. And the first case that I have here is the most common case of borescope inspection in automotive, which is cylinder inspection. Right? What you see here is this is a screen that a presentation that I explain what is the technique of actually doing an inspection on a cylinder with a video scope. And in this image here, this drawing, this is a representation. If you imagine that this is a cut on the cylinder, exactly on the center of the cylinder, and this here on the sides are the walls of the cylinder. This blue part here is the piston, and here on the top you have the head of the cylinder. That's more or less how you do an inspection on a cylinder. And here you have like this clear gray here is the video scope probe, and this green is where the video scope is looking. So in this case, for instance, I'm going to the top. I go, for instance, from a injection, the injection hole, and I put the probe here inside. And on this side, on this case here, I'm using a side-facing tip. It's a tip that looks at 90 degrees in comparison to the probe direction, and I'm looking here at my this cylinder wall. Then here I articulate my probe 90 degrees and I'm able to inspect the piston. So for instance, if I want to see the whole piston here, I can just rotate my video scope and I'm going to be looking at this area of the piston. And then I can also articulate 90 degrees to the other side and have a view of what would be the head of the cylinder. And also I'll be looking at the valves here. So this is just to give you a brief understanding of how you would use a video scope, how you maneuver the probe inside the cylinder. There is also another type of inspection, the same thing on the cylinder if you use a direct facing tip, so a lens that instead of looking to the side will be looking directly towards the piston, and which is to see a little bit more detail. But I would recommend, in fact, if you guys want to see more details about cylinder inspection, you can go, there is a webinar on the world page about this one as well that goes into detail. But what I would like to show to you is a video of this, how this inspection actually works in real life. What I'm going to show here is just a video. We're going to go through the ignition port on a cylinder. So this is the image directly from the video scope, right? So I'm going here with a video scope. Oh, sorry about that. Let's go back to the video. I'm going here to the ignition port on an engine. And what you see here, for instance, here I'm looking straight to the top face of the piston, right? So this is what I'm doing here with a video scope. Now I start to manipulate, I start to articulate. And then, for instance, I articulate, I'll go closer to the piston. I can see details of the deposits on the piston. And now I articulate. And what I'm seeing here is the liner of the piston. Apologies again with the video. Let's just jump to the point. So now, for instance, I articulated my video scope and I can see the liner, which is another important area of the inspection. I keep manipulating my probe, looking at details of the cylinder. I'm going to jump a few seconds. And now what you're seeing here is I articulated my probe, the full range of articulation, and now I'm 180 degrees and I'm looking up with my probe. So what I see here is actually the valve and the head of the cylinder. So this video gives you an idea of the type of inspection, what means to inspect a cylinder with a video scope. Okay, we have like plenty of other examples as well, but this one's just to give you a taste of how an inspection of a cylinder looks like. Okay, so now I'm passing on. So that's the first case, cylinder inspection. Now passing on to the second case. The second case is not, for instance, on the cylinder inspection is something that you do once your equipment is in service, right? Your automotive or you're doing research, but that's already running. The second case, the remote vision inspection, is called burr measurement. This image here that we see on the left is an image of a burr. The burr, what we see here, is a defect, is a residue, is a side effect of drilling operations, right? So when you drill a metal part, inside of the part that was drilled, you can have this extrusion of material, this extrusion of metal. And something that very commonly customers in the automotive sector ask is, can you measure the size of these burrs? Because depending on how big they are, you need to do a procedure to remove them or correct them somehow. And what we see here, so the left side is an image collected with a video scope of a burr. There are two images here because what I'm using here is a technique called stereo measurements. So this is a technique that instead of only observing something, I'm actually going to measure something. And here on the right side, I activated this measuring mode, right? So I'm using a video scope that's capable of doing this measurement. And what I see here is that the size of the burr, the penetration of the burr from the surface here is 1.3 millimeters. On this case here, it's a very large burr, right? I would say it's a critical case in this case because the burr is so big that is quite obvious. You probably wouldn't, just seeing that and that size, you probably would know it's a big burr. But there was another case with another customer where the burrs were much smaller and it was much more, let's say the decision criteria was much more and much narrower. And on this case here, again, I'm using a video scope here. So I have the image from the burr from here. So that is the edge of a part that was drilled. And what I'm doing here, I'm trying to measure the size of that small part there, right? Because it was the customer concern was, okay, how big are these burrs? Do I need to do anything with them? Because that might incur costs, it might incur you're doing work to remove them. Or a common case is like the customer is concerned that once this part is in operation, that little burr detaches and then goes damage another part downstream. So again, on this case, the burr was much smaller, but we still managed to do a measurement on that and provide to the customer some assurance of how big the burr was. So that is the second case. The first case we saw cylinder inspection, so that is more into service. Second case here is about manufacturing, so burr measurements. The final case for remote vision inspection is again back on the manufacturing side, is inspection using ultraviolet light. So very common case as well in many industries, also in the automotive, is to use, for instance, penetrant particles to see where you have cracks, where you have deposition and defects. And what we're going to see here is a video scope that actually uses, instead of visual light, we're going to use ultraviolet light. So what we see here, the customer had this sample here, right, that they wanted to investigate using penetrant particles. So this is the sample. And what we here you see the user is holding the probe, the insertion tube of the video scope. So that is the probe that goes inside. And you see here on the right side, the image of the video scope, right? So you can see quite clearly here from this screen. So the user immerse this on penetrant particle solution, and here you have, so you need to prepare, of course, if you're going to use UV, you're going to need to prepare your sample, and using the UV source, you're going to be able to very clearly see where the particles are attaching. Again, I have a good video to actually to show how this looks in real life. Let's just start the video here. So what we're going to see is a video of the probe going inside the sample and the image directly from the video scope. All right, so again, sorry about the issue with the video. Right, so what we're seeing here, you're going to see like fluorescence where the particles are attaching. And the fluorescence happens because of the UV source. As we can see here on the left side of the screen on the video, let's go a little bit further on the inspection. One thing to notice is, of course, when you're doing UV inspection, the light, the intensity of the light is smaller than when you're using a white light, right? So that is normal anyway. But still, if you're using, for instance, penetrant particles, you can see very clearly here, for instance, these green parts, those are where the penetrant eye is, the penetrant particles have been attached, deposited. So you see like that kind of like cylindrical sample, you go inside with the video scope and then you can clearly find where things attached. So that is the third case really that we had with remote visual inspection. So as I say, the borescope inspection, the use of video scopes in automotive is very flexible. The most important case definitely is cylinder inspection. That's where, let's say, the most traditional use of the technology was. But also you have here the other case, the burr measurement shows how video scope measurement can be used on automotive. And the last one, this third case here, is ultraviolet inspection. So it's video scopes are very flexible. You could give another example like in batteries or so on, but that is just to give an idea of what we can do with them. So now what I'm going to do is we're going to pass on to my colleague Angelique. So Angelique, I'm going to give you the controls of our presentation. Just bear with me a second. And now you should be able to operate these slides. So Angelique, it's up to you now.
Yeah, so I hope the sound is okay. And let's see if I can you see what I'm doing on the slide and moving the slides?
Yes, it's working.
Okay, so thanks, Bayard. So we wanted to cover different technology with this webinar to show you everything that we can implement, and NDT and RVI are quite complementary anyway. So here I will just explain quickly what is NDT in general and the different technology that we cover within evidence, and also how they could be applied, at which stage they could be applied within the automotive industry. And as Bayard presented, I also have I picked three application cases to go through, but there's many different ones. So stay tuned if you want to know more. You have access to the questions, and later on you can get in touch with us. So NDT is non-destructive testing. So basically any technique that is used to look inside a material, a structure, to look for discontinuities such as cracks, voids, corrosion. That's the kind of things we generally look with NDT. And there's a lot of different techniques used in the industry. We mostly cover two techniques, ultrasonic testing and eddy current testing. So ultrasonic testing, we send ultrasound inside the material from one surface, and we are looking for anything within the structure. Every material has a different property, so the sound path, the sound wave will travel faster or slower depending on the material. And as soon as the sound is encountering discontinuity, it will bounce back to the transducer that will be picked up by the instrument, and that's how it works generally. So ultrasonic testing is mostly for volumetric inspection, in comparison to eddy currents, where we use electromagnetic techniques, where there the probe is powered with an alternating current, and when moved towards a conductive material, it will create eddy current at the surface of the material, and we are looking at changes in the magnetic field around the probe. And that is more a surface type of technique that we use also. Okay, so basically the techniques and the application are selected based on material property, obviously the geometry and what you need to inspect, but also what you expect to find. You need to know a bit about what you want to be able to discover, so you can better select the technique, and within the technique the right tools also to look for the discontinuities. But overall, for automotive, the NDT can be used at several stages throughout the process. So obviously on raw materials, we can ensure that the materials are sound before they are used for manufacturing and assembly. During the manufacturing stage of the different component and the full assembly of the car also, and afterwards in maintenance, NDT can be used also to look for specific damages or flow that can occur within the structure, and that would need to be looked at regularly in order to make sure that it can be still used on a day-to-day basis. Okay, so I tried to put in two slides the panel of instruments and solutions that we have. Obviously, for NDT, every single time a solution is not just a device, but it's also the probe that you use and the different accessories, scanners, and other parts that you can have to help with the deployment of the technique. But we can look at it in different segments. So we have what we call the thickness gauges. Those products are mostly used, are ultrasonic based, and they're used for thickness measurement of parts. And also for corrosion. So you look for any thinning in material that resulted from a corrosion, or you can have a precise measurement. I will come back to that during one of the application cases. The other product segment would be flow detectors. Again, here we have two types, ultrasonic flow detectors and eddy current flow detectors. So those ones are open instruments, so you can set up a big panel of different applications and use different probes for a specific need. So for instance, eddy current is used in automotive for conductivity measurement, material sorting, crack detection, and ultrasonic can be used for looking inside the volume, detection of corrosion, voids, cracks, also welds, that kind of application. And alongside those, we also have what we call advanced solution. So based on the same type of techniques, ultrasonic and eddy current, we have advanced, and it's mostly what we call array solution. So it's powered UT and powered eddy current, where within one device and one probe we have several elements, so we can cover a lot more area in one specific path, and it's a bit more powerful. So for instance, with eddy current array you can go a bit deeper in materials, and with phased array and TFM you can see a lot of things in the material as well. And for those we have also dedicated scanners and probes that have been developed specifically for the instrument and different applications. So now moving on to the automotive industry and where NDT can help. Basically, the main challenges and driver are the productivity and ensuring quality and safety of using the parts. So NDT can be easily integrated in the manufacturing process. Also, the data are digital, so it's easy to trace and keep track of what's been done as the inspection, and also you can digitize some of the processing. So it fits well within this industry and the needs. So the first case I wanted to cover is paint characterization and integrity. We recently launched a dedicated thickness gauge that provide very high frequency measurement, and that enable us to measure very thin materials. And when I talk about thin materials, I'm talking about microns. And that thickness gauge, we launched it in March, and it can be used for instance, for paint assessment. So typically in automotive, you on a car, you have several layers of paint that goes from the primer, the base coat, the color coat. And obviously you need to control the thickness of the paint that you apply for economical reason, but also for protective reason of the structure. So with this, basically, we are able to measure 40 microns of steel and even smaller thicknesses of paint and coatings. And the other powerful things about it afterwards is that you can measure more than one layer at a time. So within the process, you could do a measurement at each layer, but you could, instead of doing that, control the process at the end once you've painted it and measure the different layers in one single go. So you would put the probe to the surface, have the right setting, and be able to, on the screen in one measurement, have access to the thickness of each individual layer and the total thickness of it. And on top of that, you would have the capability also to set up where you would put the measurement points. So alongside the instrument, we have a dedicated software that helps to define how to do the measurement and where to do it. So here are some examples of, for instance, maybe you don't see it well, but here on the part, we say, okay, you're going to inspect the paint on this door, and you can see that there's spot check to be done. So we have several points here. So the operator would know automatically where to do the measurement, could go take the measurement, and then have an automated grid filled in and report. So as a traceability and data management, this helped to streamline the manufacturing process. Another case is weld inspection. So in automotive, there's spot weld that is being used to be able to assemble 2 or more layers of metal together. And basically, when it's done, the weld quality and the weld shape depends on the welding tool that you use, the welding time as well, and the different parameters of the process, so induced current. Based on that, you're supposed to have a good weld, and you should be able to use it properly. But in some cases, the process can vary, some setups can change, and you might end up with some issues with the quality of such weld. Issues could be lack of fusion, undersized weld, and what we call also stick weld. So I'll go a bit deeper into that. Here you have some example of a good weld on the top left corner, where you have 2 sheets of metal linked together with this weld. And what can happen is that depending if you have the right parameters, you might not have a full bond, and we call it unwelded surface. So they might, basically you have no bond between the 2 layers. Another one would be to have undersized nugget. We call the weld nugget. So in that case, you still have the layers bonded together, but they won't stick together for as long as they're supposed to be as designed, because the nugget is too small, and if you put too much stress to it, then the assembly can open and be damaged. And the other one called stick is where you have a weld, and the layers are bonded together. The nugget is the right size, but the weld is not strong enough. And again, the assembly won't last the time it's designed for. So a way to look for that would be to use ultrasonic testing. And here is a schematic of the probe being used. So basically, you select the probe to fit the diameter of the nuggets. So if you have smaller weld or larger weld, you adjust the probe that you use. Usually it's used, we use high frequency probes, and ultrasonic is being sent from one surface inside the weld, and we look at the pattern of the UT beam. So moving on to the next slide, I'll show you some example here. So basically, we usually use a good weld, the weld that we know is good as an example. And within the device that we use, the ultrasonic flow detectors we have, the epoch, we set up a template. So we have a good set of parameters, we have a good signal here, and we say, okay, this is the reference. And now we'll use the same probe and the same setup with on different welds, and we'll look and do a comparison with this. So basically now I have here another type of weld, and so it's another type of weld that is the one from, sorry, I cannot go back to, it's a non-welded one. So basically you have the two layers, the signal is going through, but because it's not welded properly, the signal sent is bouncing back too quickly. So that's what you see here on the signal on the screen. You see that the peak, the green signal is the live signal, the blue signal is the template, and basically the wave is coming back quicker than what it's supposed to be. It means that there's no weld there, and it's unwelded. Another example here is when we say it's an undersized weld. Basically what will happen is we send the wave inside the weld. Part of the weld, part of the signal will go through the weld and will have a normal behavior, but the rest will be outside of the weld and will go through the first layer, bounce back and come back to the probe quicker than through the weld. And you end up with a mixed type of signal. Some signal is coming back from the single layer, and some signal is coming back from the part that is welded. So again, you can see that there's a real difference between the two signal, and something is wrong. And last example is when it's a stick weld. In that case, again, you have a real difference, and you can say that something is not good. So basically, the wave is going through the weld. You still have a signal bouncing back from the bottom of the weld, but because the weld structure is not correct, it's not the right grain structure, you do not have the same attenuation of the UT. Of the ultrasound, and the signal that bounces back is with a higher amplitude. So you can see here it's above the 100% high screen, and it's not supposed to be there. So this process is easy to learn. Once you have the right setup, the right probe, then anybody can look at the signal and tell when there's a difference, and can just notifies there's something wrong with the weld, and then you can go through multiple weld along the assembly quickly, and you can rapidly classify good, bad weld, and come back to it for another type of assessment. Finally, the other case I wanted to go through, and I'll try to finish quickly, is bonded structure. So more and more bonding is used on assembly in cars to avoid other type of assemblies, such as the Scots weld that I mentioned. You cannot use it on every structure or every area, but in some cases it's good. And because you don't manufacture any holes or any, you don't play with the integrity of the metal sheets directly, then you avoid having corrosion, for example. So in some cases it's a better assembly, but you need compromises. And that can be found on doors, hoods and trucks as well. But again, something can happen during the manufacturing process, and you can get some contamination resulting in voids, and in which case the bond quality will be damaged, and you can also have some issue with the application, or let's say the way the adhesive is put on the assembly, and you can miss some adhesives. So in that case, again, the structure is not sound the way it should be. It won't last for the time it's designed for, and that needs to be found quickly. So here I have some example again, of ultrasonic testing. The proof of concept was done manually with conventional ultrasonic testing. And in this case, basically you, again, like for the spot well, you put the probe on the surface with some coupling, you look at the signal, and to obtain an image like this, you have to raster scan, so move the probe back and forth in 2 directions, try to obtain a full mapping. So this was mostly to prove the concept that ultrasonic testing could be used for this type of inspection. It was successful, but as you can see, the image is not great. It's quite difficult to interpret, to analyze, and moving the probe back and forth, then you can also damage a bit the surface. So you need something a bit easier to implement. So we moved from conventional to array solution, and in this case you see the probe is bigger because it's like having several small probes inside, and in one single pass you can cover a larger area, and that's what you see here. In this case you can imagine that the mapping is easier because you can see straightforward something is varying here. You move from blue to yellow to red, so you know something's going on, and then you can assess. A UT expert would be able to assess and tell you, okay, there's a lack of bonding, there's a lack of adhesive here, it's not responding the way it should do, and you can adjust. And so we saw the benefits of using a resolution, but again, it was a manual scanning. So also you cover a larger area in one go. You still need to move the probe back and forth because it's a larger assembly than the probe size. So the development was made to have a proper solution that won't damage the surface. So we needed a smooth connection to the surface, and that's the type of solution that was designed. So basically it's based on array, ultrasonic testing array, and it's designed just for the edge measurement of bonded assembly, and you can go there and scan. So it's kind of a wheel that you can move along the structure, and you have a direct assessment. And you see here that you have a mapping, and again, some additional color palette can be used. So you have a green and red type of signal. So you know, red, you have an issue, green is okay. So then, because it's also encoded, you can come back and say, okay, at that location, I have an issue. You can mark the structure directly. So that's it for me on the NDT side. Thank you very much, everyone. I will hand on to Bayard for the question parts.
Angelique, fantastic. Thank you very much. I'm going to take now control back here from my side.
Okay.
So yes, thank you very much for everyone. So that is the presentation. Now we're going to go to the live questions and answers, right? So let me go back here. There you go. Let me check here what we have. But to be honest, like the first question that I have, Angelique, it's something to do with NDT, which is, can you automate any of these inspections that you show? Can you integrate that with anything in terms of like robotics or anything like that?
Yeah, that's a good point. In fact, we can almost automate any type of application. We usually start with manual proof of concept, and then depending on the technique that you decide to use or that is more appropriate to use, you face different type of challenges. So, for instance, ultrasonic testing, you need coupling between the probe and the surface. So sometimes it's water, sometimes it's a dedicated couplant. So you can automatize, but you need to find a solution to irrigate the surface. But you can imagine having the probe at the end of a robot or cobot, and get the scanning done by that.
So in the end of the day, it is possible, but it requires a little bit more of, let's say, integration with other things to be able to work.
Yes, you need to ensure that you have the good signal coming through. That's all. So
Okay.
some consideration to take.
Okay. The other question is applications to electrical vehicles, right? If there is anything, this is a question that we can discuss also from RVI, but I would like to ask first about NDT. What's the application NDT for electrical vehicles?
First, it would be similar as the current inspection that can be done on structures. We imagine that electric car needs to be lighter, so probably more bonding structure, so right to the case 3 that I showed. And towards the manufacturing stage, all about also batteries. And NDT can be used on batteries as well to ensure that it's manufactured the right way, and you don't have to do a lot of destructive testing to prove the manufacturing process.
You see, it's interesting because I think for the NDT technologies, there is just a kind of a clear case, but on the case of the RVI, the boroscope technology, the EVs, the electrical vehicles, especially the fully electrical ones, they are very different in terms of inspection because you don't have an internal combustion engine. And the first case that I shown was inspection of a cylinder, which doesn't exist on the electrical engine. So for videoscopes, it changed quite a lot of the work. It changed the nature, like the batteries and the electrical engine. They don't require as much as inspection as the combustion engines. Another thing that it's interesting to mention on the RVI side, on the boroscope side, is the type of probe, diameter of probes that used. Generally speaking, when we doing boroscope inspection, we prefer to have larger probes, more light, better image. But on the case of automotive, the rule of the thumb in general is to use a 4mm scope. And that is because of the size of these injection ports that we go through. Generally, they are small, and then you cannot really go with a 6mm. So rule of the thumb, if you're doing automotive, probably you need a 4mm scope. And the last question really that is here is people ask about the intensity of the UV light source, right? Because if you go to the standards to apply to use UV source and penetrant particle testing, you have to have a certain intensity of light to be able to use it. And then there is not one answer for this, because the intensity will depend on how far you are, which means your working distance, and also will depend on the type of lens that you're using, because depending on the lens, that will block more or less UV light. For us, the important thing is the videoscopes that we have, the light source that we have for the videoscopes, they will meet the most important standards for penetrant particles like ASTM 1417 and also the ISO. The ISO, I can't remember now the number, but the light sources that we have, you're going to be able to meet these standards. Don't see it. I don't know if anybody has other questions. Like, if I don't have anything else here on the question box. So if there is nothing else more, I'd like to thank Angelique. Thank brilliant participation. Thank you very much. And I would like to thank everyone that attended. As I say, this webinar will also be recorded. So if you want to watch on demand, we can just go back to the website, and you're going to be able to find on the Learn session, go Learn and Webinar, and you're going to find the link to the record. So again, Angelique, thank you very much. Thank you very much, everyone.
Thanks, Bayard.
And I'll see you all soon. Thank you.